is Natalie Savage, and I'm here to bring you yet another episode of 300 Seconds of Science. This time, we'll be talking about the majestic wonder at our poles, Earth's auroras, otherwise known as the Northern and Southern Lights. The name we give the Northern Lights, the Aurora Borealis, was coined in 1619 by Galileo, and this name was given in reference to Aurora, the Roman goddess of the dawn, and Boreas, the Greek god of the north wind. That said, Galileo did not discover the auroras, as the earliest suspected record of the Northern Lights dates back about 30,000 years to a cave painting in France. Many civilizations have created their own records of them since then, though the science of the auroras wasn't theorized until near the start of the 20th century. Norwegian scientist Krista Bergla was one of the earliest people to offer up a scientific explanation to the Northern Lights, proposing that electrons from sunspots cause the lights after being guided to the poles by the planet's magnetic field. Which is correct! However, this was not realized until after Bergla died in 1917. So here's how this works. Basically, the sun ejects small charged particles 24/7. These charged particle ejections create something called solar wind, which speeds away from the sun at anywhere between 250 and 500 miles per second. When the solar wind collides with Earth's upper atmosphere, the ionosphere, the aurora is created. Thankfully, due to our magnetic field, we are kept safe from these collisions, and these particles are diverted to the poles where the magnetic field is weakest. According to astronomer Billy Teets, the director of Dyer Observatory at the Vanderbilt University in Nashville, Tennessee, the energized particles of solar wind mentioned before interact with the atmosphere, transferring energy and causing the atmospheric particles to, as he called it, fluoresce. In the northern hemisphere, this produces the aurora borealis, while in the southern hemisphere, we call the lighting event the aurora australis. But why does our atmosphere produce a colored glow? Well, that question can be solved by examining the chemical makeup of the Earth's atmosphere. Our atmosphere is made up of many different kinds of atoms like hydrogen, nitrogen, or oxygen, and molecules like carbon dioxide. Each of these atoms or molecules absorbs and reflects its own set of colors. Therefore, when certain types of atmospheric elements are struck by the solar winds, certain colors are radiated from the interaction. The pale yellow-green color is produced by oxygen molecules 60 miles above the Earth's surface. Nitrogen produces blue or purplish-red auroras, and rare, all-red auroras are created from collisions with high-altitude oxygen up to 200 miles high. The brightness of the colors, however, is controlled by solar emissions. While solar wind is constant, there are sometimes lulls in solar activity compared to other times where the Earth might be overwhelmed with vast amounts of solar activity. When this uptick of energy happens, the auroras grow brighter and more frequent. From our perspective in 2023, the National Oceanic and Atmospheric Administration, otherwise known as NOAA, reports that the last such time was in 2014, and the next period of peak activity will be in 2025, as the sun's emissions operate on an estimated 11-year cycle. However, it is not only planet Earth that has auroras. Other planets have them too. All that's needed is an atmosphere and a magnetic field. Because of this, astronomers were not surprised to discover auroras on all of the gas giants, since Jupiter, Saturn, Uranus, and Neptune all have very strong magnetic fields. Because Jupiter's magnetic field is 20,000 times stronger than Earth's, Jupiter's auroras are brighter than ours. While seeing Jupiter's auroras with our own eyes would be impossible for the average person, we can certainly see them on our own planet as they occur rather frequently. 24 hours a day, 7 days a week, 365 days a year in fact. The trick is finding a good time and place to see them, especially the aurora australis, whose visible zone is mostly concentrated around Antarctica and the southern Indian Ocean. The best time of the year to see the northern lights is between September and April between 9 p.m. and 3 a.m., keeping in mind that a full moon might make it difficult to see due to the increased light. You also won't be able to see it through cloud cover, so check the weather. The best place to go see the lights is in the auroral zone, a 1,550-mile radius of the North Pole. While it's better to avoid city lights, it's safest and easiest to visit areas like Fairbanks, Alaska, Yellowknife, Canada, Svalbard, Norway, Abisko National Park in Sweden, Rovaniemi, Finland, and anywhere in Iceland. You can also check the aurora forecast from the University of Alaska Fairbanks Geophysical Institute or through NOAA. And there you have it. If you enjoyed today's content, be sure to like us on Facebook, subscribe to our YouTube channel, follow us on Twitter, and give us some love on Instagram at ZTV 300 Seconds of Science.
This program was produced by ZTV at the University of Akron. Do you want to gain experience in video production, professional social media, or working with real clients? Visit the UA School of Communications online or follow us on social media to learn more. ZTV, make media, make a difference.